be 0 and 2 copies are saying that bit should be 1. So then in that case, we have to take the decision randomly. So that's why for repetition code, we usually go for the length which is odd number. So if I consider R5 now, for R5, at least 3 bits should be in error. Then only one particular bit will be erroneously decoded. So probability of error will be like this: 3 bits are in error, 4 bits are in error, or 5 bits are in error. So if you sum up all these probabilities, this will become 0.009, which is even reduced from this particular value to this. So what is happening? Instead of sending 1 bit in for R5, instead of sending 1 bit, we are sending 4 additional bits. So that means the amount of redundancy is increasing. So as the amount of redundancy increases, the probability of error decreases. So this is the observation. So but question is, have we lost something? Yes, that is true, because as the amount of redundancy increases, the rate of the transmission scheme reduces. So this table shows, the probability of error versus rate trade-off. So without coding, the probability of error is 0.1, the rate of transmission is 1, which R3, the probability of error is 0.028, and the rate of the code has reduced from 1 to 1 by 3, and with R5, the probability of error has improved to 0.009, and the main concern is that the rate of the coding scheme has reduced to 1 by 5. Okay. So this figure, if you look at this figure, this x-axis shows this rate of the coding scheme, and the y-axis shows this probability of error. So which R1, this rate is equal to 1, and the probability of error is equal to 0.1. With R3, we move to the lower rate region. So this rate will be equal to 1 by 3, and the probability of error, this value will be 0.028. So as we increase, we move, the probability of error reduces, but the main concern is that the rate also goes very less. So if you consider, if I consider R15, so the rate will be equal to 1 by 15, and the probability of error is equal to 10 to the power minus 15. So the problem is that, before Shannon's remarkable paper in 1948, the belief was that the rate must be, vanishingly small. Then only we can achieve a negligible probability of error. That means the probability of error will be negligible only if we do not transmit anything. So that doesn't mean that doesn't make any sense, because we have to transmit at a non-zero rate. Okay. At the same time, the probability of error should be negligible. So we have to operate somewhere in this region. These are the more useful region of the rate versus probability of error plot. So before 1948's paper, the belief was that R should goes to 0, then only probability of error will go to 0. So this was the belief before 1948, Shannon's paper. But after that paper, Shannon shows that if R is less than some quantity known as channel capacity, then probability of error goes to 0. It is possible to devise a coding scheme so that the probability of error can be made negligible. The condition is that rate should be less than a quantity which is specific to the underlying channel known as the channel capacity. So if you look at this repetition coding curve, so this is the curve. However, Shannon showed that the curve is more like this. This is, for BSC with crossover probability 0.1, the capacity will be equal to 0.53. So the R should be less than this only. So this part is like, if it is possible to devise an error correcting scheme so that 0 probability of error is achievable. However, if our rate is greater than this capacity in this region, it is not possible to achieve zero probability of error. So this is, I mean, one of the remarkable result of that Shannon's 1948 paper. So again, I mean, initially I have given you a flavor of this, the importance of this information theory. Yeah, information theory. Nilakandan, I hope I'm audible, right?
Yes, Kuntal, you are audible.
No, it's sometimes difficult to know whether I'm live or not.
The video is not seamless. Maybe you have some lesser bandwidth. So that is not going in synchronized with your talking and the presentation. Nevertheless, your audio is clear and your slides are pretty much visible.
Okay. Okay, so okay, I'll continue then.
Yes, please go ahead.
Yeah, fine. Yes. So before going to the main topics, let us briefly go through this the main concepts. The basic concepts of information theory. So I'll start with the entropy. So consider this event. Then the random variable x is taking a specific value small x. Okay. So the amount of information content associated with the event x equal to small x is defined like this: log of 1 upon px. Px is the the probability mass function. So why log? Log is used because whenever we have a joint event and if the random variables are independent, then the information should be we should be able to sum the information. So log of the product will be equal to the sum of the log values. So that's why log is used to to denote the information content associated with the particular event, and it is 1 upon px because the amount of information or the amount of new knowledge that should be inversely proportional to the the probability of occurrence. So this is only the amount of information content associated with the event, with this particular event only, with a specific value of small x. So this is a certain kind of the random variable only. So if you take the expectation of this random variable, so h of x is one random variable. So if you take the expected value, that means we take the averaging of the this function h of x. Then that average is known as the entropy of the random variable x. So formally, we can have this definition: h of x is equal to expected value of negative log px. So yeah, so this is the definition of entropy. Now, what does it mean? What is the physical significance of the entropy of a random variable? So actually, sometimes we should use the word average, but I will not use the word average now. And h of x is upper bounded by log of the cardinality of the alphabet, and this upper bound is achieved only when this probability mass function is equally likely or uniformly distributed over the alphabet. And now let us consider one binary random variable x. So it takes two values 0 and 1. It takes 0 with probability p, and it takes value 1 with probability 1 minus p. So for this binary random variable, the entropy is given by this. So this is a function of, it is to be noted that the entropy is a function of the probabilities only, probability mass functions only. It is not a function of the values. So if you plot this binary entropy curve, so you will notice that this is p. So the small p is, so we have plotted this binary entropy versus the probability of 0. So if p is the probability of 0, so if p is equal to 0, that means we are very much sure that the value is equal to 1. Okay. And if p is equal to 1, we are very much sure that the value must be equal to 0 without any doubt. So if you plot this binary entropy function, so it is this function, okay? This function, okay? And the maximum is obtained. Maximum is obtained at p equal to 0.5. That means at p equal to 0.5, we are completely unsure about the value. So that means we can actually interpret this entropy of a random variable h of x as a measure of uncertainty regarding the random variable x. Okay, so this is the physical significance or physical meaning of the entropy of a random variable. So if the entropy of a random variable is very high, that means the uncertainty about that random variable is high. So for polar coding and all this in our communication system, so usually we denote this X as a transmitted symbol, and the Y this is your noise, Y is the received symbol. So that's why we have to study two random variables, or the entropy associated with two random variables. So usually we will denote X as the transmitted bit, Y as the received bit. And the detection problem is that we know this guy Y. From Y, how to find X? So this is the problem of decoding or detection. And one probability rule will be used. So I'm again revising these basic concepts. I'm sure you know these things very well, but for the sake of to understand the polar codes in a better way, I'm just going through these basic concepts. The probability rule is that if P of xy, this is a chain rule of probability, and if this is equal to P of x into P of y given x, so we can actually consider this as a probability mass function or the probability density function if the random variables are continuous. If x and y are independent, then this joint probability mass function is equal to the product of the marginal probability mass functions. So we can define the joint entropy of x and y. So the underlying probability function will be joint probability mass function. This is your joint probability mass function. So instead of using the individual marginal probability mass function, we have to use joint probability mass function. And if the random variables are independent, the joint entropy will be additive. And as I said, the detection rule is that we know the receive value. Then we have to estimate the x. What was the bit that was transmitted? So we have to study this conditional entropy. That means, given y, what is the uncertainty left in x? Okay, so this is the given event that y is taking a specific value, small y. So for that, the underlying probability mass function will be this conditional probability mass function. So you can notice that this is again, this is a function of y. So this is one random variable which is function of the random variable y. So we can average it over all possible values of y. And that average conditional entropy is known as conditional entropy of x given y. So this is the averaging we have done here. So this is the average conditional entropy of x given y, or sometimes we'll omit this word average. So we'll simply say that conditional entropy of x given y. Yeah. So again, we have to understand these meanings of these terms. What does the conditional entropy of x given y signify? So this sequence is important. So without the knowledge of y, the uncertainty of the random variable x is h of x. Suppose the receive value is not available to us, then what is the uncertainty regarding the transmitted bit? That is simply h of x. Now y is revealed. That means we receive something. We get the received signal. Knowing y, the average uncertainty left in x is h of x given y. So this is the significance in terms of the communication problem. So conditional entropy of x given y is the average uncertainty left in x after knowing y. And it can be proved that this conditional entropy is less than or equal to the entropy. That means if we know y, that cannot increase the uncertainty of the random variable x on an average. So all these terms are average only. And if x and y are independent, of course, then the knowledge of y cannot influence or cannot reduce the uncertainty of x. In that case, the conditional entropy will be equal to the entropy itself. Okay, so we can skip this example. Yeah. And the most important term, for polar code is the mutual information. So how much information y can convey about x? Y is our received signal, x is the transmitted signal. So we want to, measure this information. So what is the information and what is the amount of information that y can reveal about x? And this information, can be related to this entropy and conditional entropy. So h of x is the, as I said, h of x is the uncertainty of the random variable x without knowing y. And this is the uncertainty left in x after knowing y. So this difference is the reduction of uncertainty about x after knowing y. Okay, so this mutual information I of x, y between x and y is defined as the reduction in uncertainty about x after knowing y. Okay, so this difference is known as the mutual information between x and y. Okay, so this notation is like this. Okay, so the mutual information is symmetric in its arguments. So it's mutual information between x and y is equal to mutual information between y and x, and it can be diagrammatically represented with the help of Venn diagram. Again, this chain rule of information theory will be important. So that's why for polar code. So this is the the chain rule of probability for two random variables only. For entropy, the chain rule is like this: the joint entropy is equal to the entropy of one random variable plus conditional entropy of the second random variable, given that the effect of the first random variable is already taken into consideration. So the mutual information is also like this. So you consider this x1 and x2 as one object. The mutual information between, you can consider the mutual information between x bar and y. Okay. So this chain rule says that we have to consider one random variable at a time. So we consider x1 here and we consider x2 here. However, here given x1 should be used. That means all the probability mass function that should be used is the conditional probability mass function given x1, because the effect of x1 is already taken into consideration. So this chain rule of mutual information will be used to understand the effect of polarization. Yeah, some examples of noisy channel. So discrete memoryless channel we will consider. So a DMC W is specified by three quantities. First is the input letters x, the output letters y, and the transition probabilities y given x. Okay, this transition probability specify the quality of the channel. For example, this channel we have already seen, binary symmetric channel BSC. Okay, so as I said, a DMC is specified by three quantities. So this is one quantity. That means the set of inputs. Second quantity is the set of outputs, and this conditional probabilities, transition probabilities. So W of 0 given 0, that means this link. This link has probability 1 minus f, and W of 0 given 1. W of 0 given 1 means what is the probability of getting y given that 1 is transmitted. So this link. So this link is also f, and it is symmetric because this guy is equal to this guy. Okay. Okay, this is one example of commonly considered noisy channel model. And one channel that we'll consider to understand the polar code is binary eraser channel. So BC is used to understand, to derive the coding principles. We always considered BC as the first channel model. Okay, BC goes like this. For BC, the input letters are 0 and 1, and the output letters are 0, 1, and one additional symbol, which is known as question mark. Question mark means eraser. Question mark means eraser. That means we have not received anything. It is completely erased. Okay. So the good thing about the binary eraser channel is that there is no link from 0 to 1 or 1 to 0. Because these links are not there, say if you receive 0, we are completely sure that it is correctly received. And if we receive 1, we know that 1 was transmitted. The problem occurs only when we do not receive anything. If we receive something, then if the model is BC, then it must be correctly received. So this is the third quantity that we decide. We fix this transition probabilities. So W of 0 given 0, W of 0 given 0 is this link 1 minus f, Here is F is denoted, F denotes the erasure probability. So this W of erasure given 0. So 0 was transmitted. What is the probability that the symbol is erased? That is F. Okay, so this is one important model that we'll consider subsequently to understand the effect of polarization. Another channel that sometimes is useful is the Z channel. So Z channel is, the input is binary, output is also binary, 0 and 1. And here, two important facts are there. If you transmit 0, it is always correctly received. If we transmit 0, there is no chances of error. And if we receive 1, then we are completely sure that it is the bit transmitted was 1, because this link is absent. This link is absent, and because this link is absent, this Z channel should be better than the binary symmetric channel. Okay. So the mutual information, as I said, the mutual information between two random variables x and y is the reduction of uncertainty of one random variable due to the knowledge of the second random variable. So this is the difference of uncertainty. So if you plug in all this expression of this entropy and conditional entropy, so finally we'll get an expression like this. Don't get into too much details of this mathematics. So this mutual information, if you look at this expression, you'll notice that there are only two types of terms. One is P of y given x, and another is P of x. These are the two types of terms that are present in this expression. So that means this mutual information is a function of this conditional probability mass function of y given x and the input distribution P of x. Now this is a channel. All these things we are writing, this is nothing but P of y given x. The W I'm writing just to denote a channel in terms of the literature of polar code. So the mutual information is a function of these two quantities only. This is a given channel. This channel, okay. So channel is a given thing. So you cannot modify the channel. And at the same time, you want to maximize this mutual information because the coding scheme should be such that the knowledge of y should reveal as much information as possible about x. So this mutual information x denotes, depends on these two quantities, P of x and P of y given x. And P of y given x is nothing but a channel which is given. So, to maximize this mutual information, we can vary only the input distribution. The input distribution we can modify. What kind of parity bit we can introduce or how many parity bits to introduce. That is under our control. P of y given x is a given thing. So if you maximize this mutual information over this P of x, and that maximum value is known as the capacity of the channel. So for binary symmetric channel, for the binary symmetric channel with crossover probability 0.1, so we can plot this capacity. Okay, P1 is the probability that the bit is taking value 1. Okay, so that the other probability will be equal to 1 minus P1. So if we plot this mutual information, so we see that this is the input distribution. Okay, and in the x-axis we are plotting the input distribution, and this is the mutual information. So the maximum value is obtained like this, 0.531. So the capacity is equal to 0.531 for binary symmetric channel with crossover probability. The binary symmetric channel. Okay, and the question is, at what value of the input distribution this maximum is obtained? So when P1 is equal to 0.5, then in that case this maximum is obtained. It means for a binary symmetric channel, and in fact it will turn out that for any symmetric channel, the input distribution that maximizes this mutual information is the equally likely distribution or the uniform distribution in the input side. Okay, so here P1 is equal to 0.5. That means both the probabilities are equal to 0.5. This is equal to 0.5 and this is also equal to 0.5. It is equally likely. If the input distribution is like this, then we achieve the maximum value of the mutual information, and that quantity is known as the channel capacity. Capacity of binary symmetric channel for any general channel, I mean, with any particular value of crossover probability f is given by this 1 minus HBF. HB is the binary entropy function. Okay. Now consider the Z channel. As I said, the Z channel is better than the binary symmetric channel because the Z channel doesn't involve one crossover link. Z channel is like this. So this link is not there. This link is not there. So this link is not there because one crossover link is not there. So Z channel has to be better. That means the capacity of Z channel should be higher than that of the BSC. Okay, and in fact this is true, and it is like this. Okay, the maximum value is 0.7628, and the maximum is obtained at P1 equal to 0.456. So what is P1? P1 is the probability that 1 is transmitted. P0 is the probability that 0 is transmitted. So P1 is not, I mean, for binary symmetric channel, it was equal to 0.5. P1 at 0.5, the maximum value of mutual information was obtained. So now for Z channel, the maximum is obtained at a value of P1 which is less than 0.5. That means we should be sending more zeros, and that is true because if we send zeros, there will not be any error. If you send 1, then there will be error. So we should be sending more zeros than ones. So that is what in that case we can achieve, I mean, the higher value of mutual information. Okay. So noisy channel coding theorem. Okay, noisy channel coding theorem already I have spoken. I mean this again in terms of the repetition code I have explained. So this is one general theorem. So this goes like this. So rate versus the probability of error plot. So if it contains 3 regions, 1, 2, and 3. In 1, it is possible to get 0 probability of error if R is less than C. If R is less than C, then it is possible to get 0 probability of error. And also, if look at this region 2. If PB is acceptable and if some non-zero value of PB is acceptable to us, then we can actually operate at this particular rate, which is greater than C. And in this region 3, it is simply not possible to transmit reliably if the rate is greater than this particular curve. Okay. Okay. So what Shannon told that, Shannon's claim was only existential proof. That means he has proved that there exists a certain codes at rates below the capacity, but he didn't drop any hint how to design the good codes. Okay, so after 1948, so people started to devise, certain good channel codes. So people started with Golay codes, Hamming codes, Riedmuller codes in 1954. BCH code in 1960. BCH codes were one of the popular codes at that time. Rich-Solomon codes 960, very powerful non-binary codes. And then in 1955, so till this point of time, Rich-Solomon, BCH, these are based on algebraic stuff. And in convolutional coding, it is more of an engineering channel coding technique than a mathematical coding technique. So people say that's why this Rich-Solomon BCH code are mathematicians' code and convolutional codes are engineers' code. And then in 1993, a specific type of code was proposed, turbo codes, which are actually some kind of combination of 2 or more convolutional codes. And it was found out that with a certain type of decoding algorithm, it is possible to operate near the Shannon limit. That means our rate of the transmission will be very much close to the capacity, but in spite of that, the probability of error will be, negligible. And then LDPC codes were invented in 1964, but I mean in 1964 the decoding rule was so computationally intensive, nobody could verify the veracity of that algorithm. But however, in 1996, after the success of turbo codes, people started to know about the benefit of this algorithm, the decoding algorithm for LDPC codes, and it was found out that LDPC codes can even surpass the performance given by turbo codes. And in 2009 only, 2009, all these codes, turbo codes and LDPC codes, are capacity approaching. That means this is your rate. Rate will be, rate will be very much close to capacity, but there will be some gap between capacity and the operating rate, at which almost negligible probability of error is achieved. So that's why these are called as capacity approaching codes, turbo codes and LDPC codes. Polar codes are the first class of codes which are capacity achieving that. That means the R is exactly equal to capacity. R is operating exactly at the capacity, and in spite of that, it is possible to get probability of error goes to 0 as block length goes to infinity. So it was mathematically provable for polar codes. So to understand polar codes, we have to understand what is polarization. Okay. So the example of polarization is prevalent in our daily life. Suppose polarization between rich and poor, polarization between in politics, right politics, left politics, religion-based polarization, then polarized characters in old films like extreme. Black and white characters were there in old films. We can consider it as like completely polarized characters. There are no gray characters in old films. Okay, so these are not good examples of polarization. However, in 2009, Erdal Arikan has proven that polarization in communication is very much desirable. So what he has proven that, so he has considered a collection of identical channels. So before going to this polarization, this thing, let me explain this thing. Suppose we have a mutual information for a kind of binary input channel. So this will lie between 0 and 1. Okay. So initially, suppose we are considering 4 channels. 4 channels, the value might be like this and this. So it is, arbitrarily distributed between 0 and 1. What does polarization will do? So our objective is that this is the extreme end of polarization. So we will put 2 bits near 0 and 2 bits near 1. So initially, the mutual information was lying in between 0 and 1. Not near 0, neither near 0 nor near 1. So we want to perform some kind of transformation so that they are located near 0 and 1. So this is one kind of polarization. So this is IW, mutual information we can consider of a particular channel. If you consider 4 channel, and if you want to achieve, the rate of the transmission should be equal to 0.5, then half part will put near 0 and half part will put near 1. And this is exactly what we will be trying to do. This is what polarization means in case of polar codes. The mutual information will try to bifurcate into, we want to bifurcate into 2 groups, near 0 and 1. We do not want the mutual information value in between this 0.5. So what Erdal Arikan has done, he has considered a collection of identical channels. And the objective is to polarize them into 2 groups. Good channels, perfect channels, and bad channels. Perfect channels are, sometimes called as good channels. Bad channels means, you cannot do anything. Okay. So this is what, he tried to do. And over the good channels only will transmit the information bits. And over the bad channels, will not transmit anything. We'll transmit the frozen bits, which are dummy bits, which are known to the receiver. Okay. And the main point is that the fraction of good channels, that means the ratio of number of good channels to the total number of channels is exactly equal to the capacity of the underlying channel. So we can use these good channels only to transmit the bits, transmit the information bits. And because this ratio is exactly equal to the capacity, the rate of the transmission will be exactly equal to the capacity of the channel. So R is exactly equal to C. And these are good channels. These are good channels. These are good channels. So the probability of error will not be equal to, probability of error will be negligible. Okay. So this is the main point regarding this polar code. Okay. Okay. So polar code, as I said, polar code is is a method to convert some arbitrary channels into easy channels. So easy channels are those channels for which coding is not required. So easy channels can be divided into two groups: perfect channels and useless channels. So perfect channels means output determines the input directly. There is no need of coding. Okay, so here if you consider this binary symmetric channel with crossover probability 0, that means this link is not there. These links are not there. This crossover links are not there. Okay, so if that is the case, the capacity will be equal to 1. Capacity will be equal to 1, and the output determines the input directly. So we do not have to do any kind of error correcting codes. So this is one example of perfect channel. Useless channels are those channels for which output is completely independent of the input. Okay, so consider this example of binary symmetric channel with crossover probability 0.5. For binary symmetric channels, we have already seen that capacity is given by 1 minus HB into F, HB of F. Now HB of 0.5 will be equal to 1. So the capacity will be equal to 0 for this particular binary symmetric channels with crossover probability 0.5. Okay, capacity equal to 0. And it can be also proven that this input random variable is independent of the output random variable. X is completely independent of Y. If your output is completely independent of the input, then no kind, no types, you cannot devise any type of coding to reduce the error if your output is completely independent of the input. So that means there is no need of coding. So this is one useless channel. Okay, so polar code is a way of converting any arbitrary binary input channels to a mixture of binary input easy channels. So some of the channels will be made perfect channels and the remaining will be made useless channels. So we'll start with uneasy channels. That means channels with capacity value between 0 and 1. Okay. Now let us try to understand the basic polar transform. Okay. So this is known as basic polar transform. So these are U1 and U2 are our exact input. Okay, so simply what you are doing, we are doing only this transformation. We are doing only this transformation. X1 is equal to U1 modulo to summation of U2. So here the modulo to summation is done here. Okay, so X1, X2. And this X1, X2 are transmitted over the channel W. So this W is actually refers to transitional probabilities only, transition probabilities. Okay, and we receive Y1 and Y2. And we assume that U1 and U2 are independent and identically distributed uniformly over F2. F2 is your binary field, GF2, Galois field 2. Okay, so this is the basic polar transform. And let us try to understand how to achieve the polarization here. Okay, so it can be proven that in the tutorial I'll show this thing, that if U1 and U2 are IID uniform on F2, then X1 and X2 are also independent and uniformly distributed on F2. So it doesn't look, very convincing, because X1 is equal to U1 plus U2, X2 equal to U2. So X1 and X2 are independent. It can be shown. Okay. So what see, two identical channels we have considered. This is one W, this is the second W. Two copies of W we have collected, and this particular term is known as the symmetric capacity. So the mutual information value, mutual information, when evaluated over the, for the uniform distribution. So the mutual information value when the input distribution is uniform over 0 and 1, then that mutual information is known as symmetric capacity. This is known as symmetric capacity. Symmetric capacity. So IW is symmetric capacity. So we have two Ws. So we have the total capacity will be 2 into IW. Okay, and the capacity is nothing but what? The mutual information value between input. This is your input and output when the input distribution is uniform. Okay, because for symmetric channel, the mutual information becomes the capacity when the input distribution is uniform. Okay, and here, see, if we move from this point to this point, or this to this point or this to this point, there is no information lost. The information loss is 0. That means what I'm trying to say, if you know U1 and U2, you can uniquely determine X1 and X2, and the reverse also is true. That means if you know X1 and X2, then you can recover U1 and U2 uniquely, because this is modulo 2 summation, because U1 is nothing but modulo 2 summation of X1 and X2, because X2 is nothing but U2. So this U2 is transmitted as it is as X2. However, U1 is modulo 2 sum with U2 to obtain X1, and then X1 is transmitted. Okay. Since there is no information loss, if we move from X1, X2 to U1, U2, so this has to be true. That means the mutual information between X1, X2 and Y1, Y2 should be equal to mutual information between U's and Y's. Okay, and then here we'll use the chain rule of mutual information. So we'll consider the first random variable U1, and we'll consider Y1 and Y2, Y1 and Y2. Yeah, so this is the conditional mutual information. The mutual information of U2 with Y1 and Y2, given that U1 is already considered, and because U1 and U2 are independent, we can put U1 like this. So what we have obtained here. So this is the main point for the main point to understand the polar code. So we have started with two identical copies of W. That means we have started with 2 of IW. And we have obtained this, this 2 of IW is broken down into two terms like this. U1, the mutual information between U1 and Y is the mutual information between U2 and Y1, Y2 and U1. Okay, so this channel I'm denoting as W minus, and this channel I'm denoting as W plus. So if I denote a channel, as I said, if I denote the channel, so we have to denote the input and output. So for W minus, the input is U1 and output is Y1 and Y2. And for W plus, input is U2 and output is Y1, Y2 and U1. So let us try to understand this two artificially created channels. So these channels are known as two synthesized channels, W minus. Y minus is put and Y plus is put. It will be apparent in the coming slides. W minus, for W minus, U1 is the input and Y1, Y2 are the output. Okay, so what is actually happening? And for W plus, U2 is the input and Y1, Y2 are the output, and U1 is also part of the output. Okay, so without polar coding, the situation is like this. Because without coding, we are transmitting U1 as it is and U2 as it is. However, with polar coding, we are transmitting U1 through a particular channel W minus. The W minus is like this. W minus is a channel for which the input is U1 and output is Y1, Y2. And U2 is transmitted over an effective channel W plus. That means because of the polar transformation, U1 sees one effective channel W minus and U2 sees an effective channel W plus. So U2 for U2, for U1, these are the actual outputs, and for U2, these are the actual outputs, and also the previously decoded output is also the one part of the observation. So at this point I'll explain now. So Y1 is a noisy version of X1. Y1 is a noisy version of X1, which is U1 plus U2. Okay, that means what was the transformation? Transformation was simple. This U1, U2, and this goes like this: Y1, Y2. Okay, so Y1 is a noisy version of X1. Noisy version of X1. X1 is nothing but U1 plus U2. Y2 is a noisy version of X2. Okay, so W plus. So W plus has a link, the original link. The original channel was W. So the W plus, see U2 is nothing but X2. U2, I mean, if you consider this transformation, this is U1, this is U2, U2 is X2, so this X2 is sent over W. So for this channel, U2 will already include this original channel W. So W plus has a link, original link W, apart from the other links. So W plus has to be better than the original link W or original channel. However, the same is not true for W minus. W minus, see W minus, what is happening? U1 is the input for W minus. So U1 is added with U2, which is completely independent of U1, and then this is transmitted over W. So this is your X1 and this is your Y1. Okay. So this channel, so this will be part of, this will be your W minus. The W minus doesn't contain the original channel because this U2 is a kind of noise for U1. Because U2 is a kind of noise, this W minus doesn't contain the original link W. This U1 to noisy U1, that link is not there. U1 to noisy U1, that link is not there in the case of W minus. So since W minus doesn't include the original channel W minus has to be worse than W. That means already some kind of polarization has already happened. We have started with two identical copies of W, and I mean we have unequally distributed the symmetric capacity so that one becomes better than the other. So after the basic transformation, this is one, frame length is equal to n equal to 2. So after the basic transformation, we can see that I of W plus is greater than I of W. This is the symmetric capacity or the mutual information when the input distribution is uniform. So I of W plus is greater than or equal to I of W, which is greater than or equal to I of W minus. Okay. However, the total mutual information remains constant. It means the total mutual information or the symmetric capacity is preserved. So the question is, these channels are real or not? Okay. So for W minus, U1 is the input and Y1, Y2 are the output. So this is a bona fide channel. So there is no doubt about it. Y1, Y2 are the real observed values. U1 is controlled by the transmitter, Y1, Y2 are observed by the receiver. However, this channel W plus, U2 to Y1, Y2. So for W plus, this is the input and these are the output. These outputs contain the real output Y1 and Y2 and one random variable U1, which we are supposed to estimate, which should be part of the input. So the channel W plus raises questions. Okay, U1 is not observed by the receiver. Okay, so in actual implementation, this U1 has to be replaced by U1 hat. U1 hat is then nothing but the estimated bit. The previously estimated bit should be part of the observation for the decoding of the second bit. That means the polar code is inherently sequential. It is serial. It is not parallel. To first decode the first bit U1 to obtain the estimate U1 hat, and then decode U2. And the effect of polarization can be understood. For binary eraser channel. Okay, so let us try to understand for this polarization effect for BEC. Okay, so W minus has U1 as input and Y1, Y2 are the output. So this table, try to understand this table. So the first column is the input, second column is the output, and third column is an yes/no answer, whether we can decode the input or not. So output contains two subcolumns, Y1 and Y2. Okay, we are considering the W minus channel, and we are considering this BEC with eraser probability F. So U1 is the input that we are trying to decode. Okay, so if Y1 and Y2 are both erased, then you cannot decode the input. So note that for BEC, as I said earlier, if you receive 0, that means it is the bit transmitted was 0 only. If you receive 1, the bit transmitted was 1 only. The problem arises only when we receive this eraser symbol. Okay. The second case is Y1 is erased, Y2 is not erased. So if Y2 is not erased, it has to be equal to X2. Y2 must be equal to X2, and X2 is nothing but U2. So Y2 is equal to U2. But U2 and U1 are independent. So by knowing U2, we cannot decode U1. So the answer is no. Can we decode the input? The answer is no. The third case is Y1 is not erased. Y1 is not erased means Y1 is exactly equal to X1 because the W is BC. X1 is equal to U1 plus U2. But as I have said that U1 plus U2 will be independent of U1. And because of that, we will not be able to decode the input. And the fourth case is that none of the outputs are erased. Okay, none of the outputs are erased. So in that case, we'll be able to definitely decode the input. How to obtain the decoded output? Simply do the modulo 2 summation of this guy with the modulo, with this U1. U1 plus U2 will be equal to U1. So this answer is yes. That means for W minus, U1 can be recovered only when both Y1 and Y2 are not erased. So for W minus, we can find out the effective eraser probability. The eraser probability F minus for W minus is 1 minus F whole square, that is equal to 2F minus F square, because the bit will be erased. Bit will not be erased only when both Y1 and Y2 are not erased. So this is the probability that both are not erased. So the 1 minus that probability will be the eraser probability of F minus. Similarly, we can look at, so the W minus will be a binary eraser channel with a modified eraser probability 2F minus F square. Okay, now let us consider the second channel W plus. For W plus, U2 is the input and Y1, Y2, U1 are the output. Okay, so we will consider the similar kind of table. Only thing is that output column will have 3 subcolumns, Y1, Y2 and U1. Okay, now first case is that Y1, Y2 are both erased and U1 is not erased. If U1 is not erased, that means we have the perfect knowledge of this U1. But U1 and U2 are independent. So U1 cannot provide any information about U2. So the question is, can we decode the input? The answer is no. Okay. The second case is Y1 is erased, Y2 is not erased. As I said, if Y2 is not erased, it is exactly equal to X2, and X2 is nothing but exactly equal to U2. That means we know U2. If we know U2, then of course we can decode the input. So here we are assuming that the U1 is perfectly available. So this U1 U1 is perfectly available to us. That's why this column doesn't contain any eraser symbol. So this, this polar code is serial inherently, and there is a problem of error propagation. So if the first bit is not correct, not decoded correctly, then the second bit and the subsequent bits also will get influenced by that erroneous decision which was made previously for the earlier bit. Okay, good. So the third case is that we know, y1 is not erased, y2 is erased. So y1 is equal to u1 plus u2. Okay, now u1 plus u2 we have, and we have the knowledge of u1. So we can sum them up. If we sum this part with this part, then u1 will get cancelled. We'll be left with only u2. So we can decode. And then the third case and the fourth case is, y1, y2 are both available to us. So we can definitely decode the input. So here, U2 is erased for this channel. U2 is erased only when both Y1 and Y2 are erased. Okay, so U2 is erased only when both Y1 and Y2 are erased. So the erasure probability will be equal to F square, F plus. F plus is the erasure probability for W plus. So F plus will be equal to F square. This is a binary symmetric channel, binary eraser channel with erasure probability F square. Okay. So what we have got? We have started with this channel, binary eraser channel with erasure probability F. 2 copies of this. Okay, 2 copies of this same channel, and out of these 2 channels, we have created one channel W plus and another channel W plus. So W plus is shown at a greater height than W to signify that W plus is better than W, and W minus is put slightly lower height compared to W to signify that W minus is worse than W. Okay. However, if you note that, if you plot this F plus and F minus, okay, so this F plus and F minus, this red one is F plus, this red one is F plus, and the blue one is F minus, and this diagonal line is F. So you can show that F plus is greater than F, and F minus is lower than F. Okay, so we can say that W plus is better than W, and W minus is worse than W. And this can be also verified in terms of the symmetric capacity. We know that the capacity of binary symmetric channel is equal to binary eraser channel with erasure probability F. The capacity is equal to 1 minus F. Okay, so the symmetric capacity for this channel is equal to like this. So it can be verified that IW plus is greater than or equal to IW, which is greater than or equal to IW minus. However, if you sum them, if you sum 1 minus F square and 1 minus 2F plus F square, then we'll have 2 minus 2F. Okay, 2 minus 2F. So 2 minus 2F means what? 2 into 1 minus F. So that means 2 into IW. So the total mutual information or total symmetric capacity will be preserved. Okay, so what we have seen for n equal to 2, how to construct the polar code we have seen. Okay, now how to extend this concept to block length which is greater than 2. Okay, so that I'm going to explain now. So the principle of this construction is that you always start with the identical copies, and you do this modular summation between the identical copies. Okay. So we'll be starting with this one copy of, we have 2 identical copies of W. From 2 identical copies of W, we'll form a pair of W plus and W minus. So this is one copy of W plus and W minus. Okay. Then we'll consider another duplicate copy of that pair W plus and W minus. Okay. So we started with 2 identical copies of W. From 2 identical copies of W, we have formed a pair of W plus and W minus. Now we have one pair of W plus and W minus. That pair is duplicated again to get the second copy of W plus and W minus. Now the XORing will be done between the similar thing. Okay. What is the similar thing? Similar here, it is similar thing is that U1 and U3 are similar because U1 will go through the same kind of channel, U3 will go through same kind of channel, and U2 and U4 will go through similar kind of channel, which are actually better than the previous channels. So modulo to summation will be done always between the similar things. So the modulo to summation will be done between U1 and U3, similar. Okay. Second, U2 and U4 are similar. So the modulo to summation will be done between U2 and U4. So we get this. Okay. So it can be said that, I mean, in this way we can find out the polar code of length n equal to 4. Okay, we have started with 4 identical copies of W, and we'll get this input bits. Okay, so this is the polarization construction. I mean, we can recursively perform the same procedure, again and again to get polar code of length, which is equal to some power of 2. It should be noted that polar codes, so the length of polar codes are always power of 2. So this process can be continued recursively. Okay, this is one example of a polar code with length n equal to 8. And now the encoding. So construction, I mean, this encoding is that, I mean, we have to select what are the information bits and what are the frozen bits. See, we have n number of bits, but we are not going to use all the n number of bits to transmit the information bits. We will put the information bits only over those bits which undergo very good channels, and for those bits which experience bad channels, we are not going to put information bits on those bits. Okay, so information bits and frozen bits. So from this 8 number of bits, so here we are considering n equal to 8. We have n number of input links. Okay, but we have to select. Out of this n number of input channels, what are the good channels and what are the bad channels. We'll be using the good channels only to transmit the bits. Okay, so for that, what we'll be doing? See, this bit goes through a particular channel. This bit will go through a particular channel. So suppose for that particular channel, this mutual information is computed like this. For binary eraser channel, the mutual information can be computed quite easily by that recursive relationship. Okay, IW plus, and we know this, right? IW plus and IW minus. We know these formulas, and using this formula recursively, because at any stage, this bit also goes through a certain kind of BEC channel only. Okay, this bit goes through a BEC channel. This bit goes through a BEC channel, binary eraser channel. So for binary eraser channel, that means even after combining this, even after performing this modulo to operation, the channel remains binary eraser channel only. But the same is not true for other channels. If we started with binary symmetric channels, or if you start with AWGN channels, this bit may not go through another AWGN channel with some different parameters. But for binary eraser channels, any intermediate bit will experience binary eraser channel only, but with a different eraser probability. Okay, so we can compute then this mutual information of this input bits. Okay, as you see, it is almost in the increasing order apart from this bit. So this fourth bit is having a very high value. Fourth bit is having a better mutual information than the fifth value. So it is not. So you cannot say that it is always serial. Okay, it has to be. It has to be computed. So suppose the rate of the coding scheme is 0.5. That means we have 8 number of bits. We have 8 bits. Out of 8 bits, we have to use 4 bits to transmit the information bits. 4 bits, the remaining 4 bits will be used to send frozen bits only. Okay, and we will be using the very good channels to transmit these 4 information bits. Okay, so we'll consider this bits. So this is having very good, very high value of mutual information. Okay, this and that. This will not consider for transmitting the information bits. Okay, so in this way, by computing a mutual information bits, we can select what are the bits that what are the locations at which we should put the information bits. Okay, this is known as the construction of the polar code, or how to select the information bits and frozen bits. And for BC, it's quite easy. BC, it's quite easy to find out the frozen bits and the information bits, but sometimes it's very difficult to I mean order the channels in the increasing order of mutual information, because we do not have the simple recursive relationship of mutual information if the channel is not, if the underlying channel is not BC. So this whole polar code, unlike LDPC code is a universal code in the sense that it doesn't depend on the channel. However, the polar code is not universal. The polar code is specific to a particular channel. Polar code, I mean the selection of this frozen bits and information bits depend on the underlying channel. If the underlying channel is different, then this ordering, this mutual information values will be different, and some other bits can be selected as the information bit. So it is channel specific. So what is the encoding complexity? The encoding complexity is, I mean, you can see that log 2 n stages are there, and there are n by 2 modulo 2 addresses are there. So this is just the complexity thing. So the complexity is of the order of n log n. Now coming to the decoding. Okay, the decoding is important for any error correcting code. So again, we will consider the binary eraser channel to understand the decoding process. So as I said, the decoding is the inverse operation of encoding. So whatever we have done in the encoder side, we have to decouple that. We have done the modulo 2 summation, and we have to decouple that thing in the decoding process so that we can recover the input. Decoding is the inverse operation of encoding. First, consider W minus. So encoding, what was the encoding? Encoding was like this. U1 is the input, W minus. U2 is also input, but we are not bothered about U2. We are not bothered about U2. So these are the output. Okay. So this is Y1 is equal to U1 plus U2. Y2 is equal to U2. Okay. Because this is binary eraser channel only. Okay. So the decoding has to be the inverse of this. So decoding rule I am writing as D minus. So I mean U1, U2 were the output of the encoder. So Y1, Y2 are the input here in the decoder side. U1 was the input to the encoder, and U1 hat is the output of the decoder. Now we have to find out this D minus. Okay, so D minus acts on this Y1 and Y2 to produce the estimate of the first bit U1. So what will be the decoding rule? D minus. Okay, for binary eraser channel it is very easy. Suppose if Y1 we can decode. Already we have seen that for the for W minus we have already seen that we can decode the input only when both Y1 and Y2 are not erased. If both Y1 and Y2 are not erased, simply we will do Y1 plus Y2. If you add this guy with this in modulo 2 fashion, then U2 will get cancelled. We will be left with only U1. So that will be estimated like U1 hat. Okay, so this is the decoding rule in the case of BC. Okay, if either Y1 or Y2 is eraser, then we cannot decode. Okay, this will be considered as a decoder failure. Now consider W plus. W plus, what is the encoding? Encoding was for the encoder U2 was the input, and Y1, Y2 and U1 are the output. Okay, so this is the rule. So decoding is like this. The same output is considered as the input here, and this input is the output here. Now we have to find out the decoder rule, D plus. Now how will you find out the U2 hat? Okay, if Y2 is, see, we have, from the table you can find out, if Y2 is not erased, If y2 is not erased, if y2 is not erased means what? We already have this u2 because y2 is exactly equal to u2. So u2 hat will be equal to y2. If y1 is not erased, then y1 plus u1 will be equal to u2 from this relationship. We assume that the first bit is correctly decoded. That's the point. I mean, if the first bit is not decoded correctly, then we are in trouble. We cannot analyze the decoder. Okay. I mean, so depending on the output of the first bit only, we're going to perform the decoding of the second bit. So this is the decoding rule. So for BC, the decoding rule is so simple. Okay, for our AWSGN, of course, I mean, in the tutorial, I'll give one, one problem, how to formulate this decoding for any general channel like AWSGN. Okay, so this is the decoding rule D plus. Okay, so how to perform the decoding then? See, so we can understand this decoding process for n equal to 4. Okay, so D minus. So D minus is used to decode these upper bits of every layer like U1, U3, or B1 or B1 and P3. So here, if you look at this upper layer means what? The upper bit of this modular summation. These are the upper bits of the modular summation. This and this, and these are the lower bits of the modular summation. So for the upper bit, we are going to use decoder D minus, and for the lower bits, we are going to use the decoder D plus. That's it. Okay. So D minus is used for the upper bit. So we get U1 hat here, U3. So this bit is estimated. I mean, as I said, I mean, decoding is the inverse of this encoding. So we have to move from this to that. So we know the noisy version of X1, noisy version of X2, like this. Now this has to be, I mean, we have to move in the opposite way. Now we'll decode these bits. Once these bits are decoded, then we'll decode these bits. Layer by layer, we'll have to move. Okay, D plus is used to decode this bit U2. U2 hat is obtained like this. Note that the previously decoded bit is also used as an input here. Previously decoded input is also used as an input. Okay. Similarly, we also use the D plus to obtain this U4 hat. As I said, the D minus is used to estimate the bit at the upper layer of every XOR summation, and D plus is used to obtain the estimate of the lower bits. Okay. Similarly, so here U1 hat, U2 hat, U3 hat, U4 hat are obtained. Now we have to find out the estimated bit of the last layer. Okay. Similarly, we can apply, as I said, P1 and P3 are similar, and they are the top layer of the modular summation. Okay, so in this way we can apply D minus and D plus recursively, and we will be able to estimate this input bits V1, V3 to V4. So this decoding rule is known as successive cancellation decoder, because we are cancelling. Why it is called successive? Because it depends on the previously decoded input. Like suppose to estimate U2, we need the previously decoded input U1. That's why it is known as successive. Cancellation because so if Y1 is equal to U1 plus U2, then U2 can be obtained by cancelling the effect of U1. That means we know U1, and we cancel the effect of U1 by modulo 2 summing itself with the Y1. Okay, so this is the you try to cancel the effect of the previously decoded bit, and the decoding complexity is also in the order of n log n. It can be proven quite easily. Now, and for 5G NR standard, polar codes have been recommended for certain control signaling schemes, and it took around 10 years after its invention in 2009 to get some concrete applications. Okay. So in 5G NR, what we do, we have one CRC encoder. That means it's a concatenated system of two coding systems, polar code as well as CRC code. Okay, and one thing has to be noted that this the length of the polar code is always a power of 2. That means the length can be 8, 16, 32, 64, 128. So if you look at this gap, so between 64 and 128, there is no polar code available. But in 5G applications, the target length E may not be the power of 2. So here this N is power of 2, but E need not be power of 2. In that case, how to bring the length N down to E? That is known as the rate matching or the length matching. So that rate matching or the length matching has to be done. And similarly, I mean, in the decoding process, I mean, this process has to be, I mean, inversed. And in the decoding side, this successive cancellation, advanced version of successive cancellation decoding is used. That is known as successive cancellation list decoding. That means we keep alive, I mean, one list of code words before committing to some already. I mean, before committing to one particular part, we maintain a list of possible code words at every stage. Okay, so how to perform the rate matching or the length matching for 5G NR? Okay, so the target length is E. Target length is E, and the length of the mother polar code is N. So N is some power of 2, but E is not equal to N. So 3 types of operations are recommended. One is punching, second is shortening, third is repeating. Okay, so what is punching? So punching is used when E is less than N and the rate is less than 7/16. So punching, so if you look at this diagram, so this is this point. From this point, your output bit starts. Okay, this goes like this. So in punching, certain bits are not transmitted. Like this for punching, it starts from this point only. For punching, it starts from this point only. Okay, so that means for punching is equal to not transmitting the bit. Not transmitting the bit means the log likelihood ratio is equal to 0. Okay, first N minus E bits are not transmitted. So if we do not transmit N minus E bits, then the length will be equal to E. Shortening is, I mean, somewhat different. Shortening is equivalent to putting the LLR equal to infinity. Okay, in shortening, what we do in shortening, I mean, the last shortening goes like this, the red line. In shortening, we do not transmit the last. I mean, we transmit the known values. We transmit the known values of the last N minus E bits. That means in shortening also, we do not transmit N minus E bits, but we put the known values. And these are known to the receiver. Because it is known to the receiver perfectly, the LLR log likelihood ratio is infinity. We have infinite amount of reliability. Okay, and since punching is applicable when the rate is small, and shortening is desirable. Shortening is applicable when the rate is high. Okay. Repetition. So this is punching and shortening are used when E is less than N. Repetition is used when E is greater than N. So the repetition is the green line. So the repetition goes like this. Okay. So the additional bits are repeated twice. So this U should be equal to E minus N. This U number of bits are repeated twice. So in this way, even though the polar coding scheme doesn't give a code which are not necessarily power of 2, through these steps of punching, shortening, and repetition, we can get polar codes of arbitrary length, which is very much desirable in 5G NR standard. So these are the bibliography. Yeah, so this is, I think this is the end of my talk. I have one tutorial, and if time permits, I can briefly go through the tutorial, and solution I'll definitely provide. Yeah, thank you very much.
Okay, thanks, Dr. Kuntal. So now I would like to know from.
Yeah, I can take up questions, or shall I just simply go through this tutorial in 5 minutes and then?
As per your wish. So once you are done, I can ask the participants if they have any questions.
Yeah. I'll take some questions then. Let us have some interaction also. Yeah, if you have any questions, then please raise.
Yeah. Okay, please raise your hand. I will unmute yourself. You can interact with the speaker. Okay, I think there are no questions from the participant side. Okay, Kuntal, you would like to?
Yeah. I'll just briefly, touch upon this. Yes. Yeah. Yes. So one tutorial is there. So the first question is about, this simple this concept that you are using, this U1 plus U2 and U2 are independent. So for that, this question is there. The second question is about the construction of the, polar codes, how to select this frozen bits and the information bits. And the question number 3 is about to derive the steps for successive cancellation decoding. Okay, for any general channel. For BC, I have already explained this part. And this fourth question is about to find out the decoding step for using likelihood ratio values. And the fifth question is about the complete example. Okay, so specific values of the received values are given, and given that how to perform the decoding. Okay, so the solution is also there. So if solution is there, so it will be easy for you to understand. So I understand that this topic may be very difficult to, to understand at the first sight itself. So if you go through sequentially, it will be, more enjoyable. And that's all from my side, Lakshman.
Okay, thanks, Kuntal. So Kuntal, I would request you to share this tutorial and the solutions in the materials in the Teams.
Oh, okay. You have one link, right? Yes.
Yeah,
yes, I'll do that.
If you go to the class materials, you can upload your tutorial.
Yes, sure, I'll do that.
So they can directly get it from there.
Yeah.
And I think you will be able to see the chat box. There are 2-3 questions. If you could address them, it will be fine. What are the merits and demerits of polar codes?
Okay. They have, yes. What are the merits of demerits of polar code? Yeah. I think Nilakandan, okay, yeah. Okay, I can see these questions now. Yeah, merit is that polar code is, mathematically it is possible to prove that it can achieve the capacity. This is one of the merit. The second merit is that polar code with CRC, when decoded with successive cancellation list decoding, it can surpass the performance given by LDPC codes. LDPC codes in the finite block length regime, it suffers from error flow problem. That means if the SNR goes high, the BER sees some kind of error flow. So that problem is not visible in the case of polar codes. These are the merits of polar codes. Coming to the demerits. Demerit is obviously the decoding complexity, because for LDPC code, the decoding can be done in parallel manner. Okay, every bit can be updated parallelly. However, for polar code, as I said, the decoding is sequential. The first bit has to be decoded, then only you can decode the second bit. If the first two bits are like this, okay. I mean, if you draw this decoding structure as a part of tree, I mean, you have to first estimate the first bit, and then you have to, I mean, decode the subsequent bits. So the error propagation is one issue in the case of polar codes. So these are the merits and demerits of polar codes. Kindly share the tutorial. Yes, I'll definitely share the tutorial. So what is the scope for research in polar codes in 5G communication? So 5G communication, as I said in the last slide, so this rate matching is very much important. So if you consider this rate, I mean, it's not rate matching, it's the length matching. The length of polar code is always the power of 2. I mean, 1632, 64, 128. Between 64 and 128, there is no polar code exists. So if I want to have a polar code between 64 and 128, what shall we do? So we have to do the punchering. Punchering means we do not transmit certain bits. The last I mean, if I want to assume that 128 is one code, and suppose I want to achieve a polar code of length 124. So we'll start with polar code of length 128, and 4 bits will puncture. That means the 4 parity bits will not transmit. Now, if we do not transmit these 4 bits, the performance will be degraded, because at the receiver we have less information available. Now the question is how to select these 4 bits out of this 128 bits. In 5G NR, it is arbitrarily, I mean, it is selected as, I mean, to reduce the complexity. It is assumed that it is considered that the first 4 bits should not be transmitted. But in literature, it is already there that, I mean, this selection is not so simple. Out of 128 bits, how to select these 4 bits so that the performance is optimized. So this selection of, puncturing bit is not so straightforward as given in 5G NR standard. So this can be one of the research area, how to design length compatible polar codes. Second area can be at the construction side. Construction side means you have 128 number of bits. Out of 128 bits, how to select the information bits and the frozen bits. Suppose your rate is 0.5. So out of 128 input bits, so puncturing happens at the output bits. So you just simply do not transmit something, and the information bit and frozen bits happens at the at the input side. So out of 128 bits, if your rate is 0.5, then you have to select 64 information bits and 64 frozen bits. So how to select the 64 information bits out of 124 bits? That also depends on the underlying channel. So there is, as I am aware, there is no general algorithm to find out this 64 information bits out of this 128 bits. So this construction of this polar code, that means how to select this frozen bits. That can also be one of the research area. Another research area is that now people are considering this 1010 only. That means modulo to sum only. So instead of modulo to sum, people can, you can consider some other kind of operations also. That means instead of using this 2 by 2 transformation matrix, you can consider a higher matrix, as well as this matrix need not be binary. That means we are doing the binary operations only. We are operating over the binary field GF2. We can operate at the GF8, GF16. That means higher order polar code is also possible. And for higher order polar code, the low complexity decoding rule is not still available. Okay, so design of low complexity decoding algorithm for non-binary polar code can be one of the research area. Yes. So what is the next, sir? Is it possible to use polar codes for underwater wireless communication? Yes, of course, it can be used. But as I said, polar code is, channel dependent. So underwater wireless communication will have different channel conditions. So you have to model the channel appropriately, and then depending on that model, you can have selection algorithm for frozen bits and information bits. But nevertheless, the basic operation of polar codes will remain same. Depending on the channel, only thing that will change is the selection of the information bits and the polar information bits and the frozen bits. Basic decoding process will remain same. The third question is, then can polar codes be used in steganography in image? Yes. I mean, in any application it can be used. So when will 5G be launched in India? What is better in 5G than 4G? I think Nilakandan can answer this. When 5G will be launched?
Yeah. So during my session, I will address that in detail. Yeah.
Yeah. So this question I'll defer it to that Nilakandan session. So apology for that. So can it be used for FSO? Free space optical communication, right? Yes, of course it can be used. As I said, it can be used in any scenario. Only thing is that the underlying channel has to be modeled properly, and we have to have a mechanism to find out this information bits and frozen bits. So LDPC codes are independent of the applications, that I mean independent of the channel, but polar code is not independent of the channel. Yes. MATLAB or Python, which is best to implement polar codes? See, I did for my work I did in Python, but in MATLAB also it is possible. In MATLAB 2018 and for upcoming versions, I think there are built-in functions available for polar codes also. But if you want to learn polar codes and the decoding algorithm properly, I would suggest you to not to use the toolbox functions. You can use this. Either way, I did this thing. For successive cancellation list decoder I did, and Python was little bit faster than MATLAB. Nilakandan, if our this faculty colleagues require Python code, I can give. I have those codes.
Okay, yeah.
If you get this request, I'll be happy to share the codes.
Okay, that's really great. So if any of the research scholars or faculties working in this area, polar coding, error control coding, drop me an email. I will get access to the code and I will get it from the speaker.
Yeah, do we need to change the design aspect of polar codes if we are doing it for 3D? 3D MIMO, okay, 3D MIMO in 5G. Yes, that answer. Yeah, I'm probably 3D MIMO. No, so this angle will be coming. Perhaps, again, I think we should look in a different way. As I said, that this decoding will remain same as it is. Only thing that may change because of the this construction algorithm, construction, how to select this information bits, that ordering. No, in 5G NR already that we have a reliability sequence is there. This in 5G NR, and that to reduce the decoding latency, one particular bit sequence is already given, a length 1024. So if you want to get a length 128 polar code, from that sequence only you can select this. Serially you can select this information bits. So, but as I said, 5G NR, a lot of things have been put there for polar codes to reduce the complexity only, not to get the optimum result. When I did some work on the puncturing itself, so in the puncturing in 5G NR, the first n minus e number of bits were punctured, but when I did the simulation, this first n minus e bits, these are not optimum punctured bits.
Yeah, to address the question from Bino 418, actually this kind of workshops are specially focused and meant for those who are working in the research area. This comes under advanced workshops, not like a basic workshop. So when participants are choosing their FDP, they have to choose the one in which they are comfortable. There will be some basic FDPs like digital signal processing or some IoT. So there they will cover from the basics. But here, this kind of advanced workshop, we presume that you have enough background in the relevant area. So that's why you have chosen this FDP. So even all the speakers will be aligned in that area. I mean, in that aspect only. Yeah. I think, yeah. Kuntal, over to
I think in this, I mean, that I understand. Polar codes, it will be difficult to understand at very first reading and very first presentation. So if you have background in information theory, then only it will be possible to. If you have not read information theory, I mean, it will take time. It is not difficult. I mean, as people say, polar codes can be taught to any high school students who know information theory.
Yeah, there are many very good books available for massive MIMO, 5G, and so probably we will. I will try to make a list.
For books, yes. For books, I can give a few good books, polar codes.
Yeah, so we will give those links in that materials of this FDP teams. Yeah.
Yes.
And Kuntal, there is one more question from Geeta Priya. Like in 5G, is it only in the physical
is it only layer? In physical layer? Changes will be in new radio. I think it's only in physical layer. Physical layer.
Yeah, and I think one of the participants, Afsar, I think, if I read the name, I think it reads Afsar. So Afsar, I will share the code with you, and Sanjay also. Like I will get the code from the speaker and share it with Afsar and Sanjay. Since I can't put it in the common platform, if you are interested, drop me an email. I will get it from the speaker. Yeah. Okay. Okay. I think Dr. Kuntal, thank you very much. So
thanks a lot for giving this opportunity. And So and also thank all the participants for attending this talk in the afternoon time. Thanks a lot. So one more question. So MATLAB code for massive MIMO. That I think a massive MIMO for MATLAB code for massive MIMO will be available. Dr. Nilakandan works in massive MIMO. So
So if you go to MathWorks, so if you go to the MathWorks website, so if you go to documentation, if you go to the resources, you can find a lot of codes regarding massive MIMO in terms of channel estimation, beamforming, whatever the application you would like to, you can get from MathWorks itself. Recent release, they have all the resources, toolbox, everything. And also I have planned one more session subsequently in the exact slot, I don't remember, where we will show you the demonstration of the 5G toolbox in the recent releases of MATLAB, so that you will come to know where to get access to the code, how to use that, how to apply them, if at all you are doing research in that area. Yeah. Okay. Yeah. Thanks. Okay.
Yeah, okay. I would have completed this tutorial also, that hands-on session also. I would love to do that with this Python code, but the time is not there.
Yeah, probably. Yeah, if some participants are really interested and they are doing research.
Yeah, we can have a separate session.
Separate session. I might
after 4 p.m. or 5 p.m. maybe.
Yeah, we can discuss with them. If really that's what the focus and objective of the FDP. So primarily, we would like to address faculty colleagues and particularly the research scholars who are pursuing research in that area. So that's why we have chosen the topic from a variety of areas in the 5G, so that those who are doing research, they should get maximum benefit. So if there are many such scholars, we can meet separately too, so that let us not overburden others. So we will invite, and Kuntal and I can join, and we can make it more beneficial. Yeah.
Yes.
Okay, fine then. Thanks, Kuntal. So just I will give them some instructions and then I will wind it up.
Yes, sure. So I'm leaving, right?
Yeah. Thanks, Kuntal.
Okay. Thanks a lot, everyone.
Bye. Okay, so now let me explain regarding the attendance and the part clearly. I repeat that. I hope all of you are here. I keep receiving the same question here and there from individuals, and I can't respond to everyone at the different platform. So let me explain clearly how that works. First point, I think many of you have given again this kind of to reactivate your link. That will be almost so far whomsoever has given, we have done for them. So I think you might have received an email by now. So those who are joining as a guest now, I think they might have given their name in the Google form. By now it is already done. So either you might have received an email or will receive soon. First point. That is to enable you to access these kind of materials. For example, if the speaker is going to share the slides, tutorial, everything, you can directly come and take it from there. I don't need to forward that to you separately. That's the only objective of that. With minimal interaction between us, everything will be in the common platform. Right. That's one point. Second point. Even though you don't have an account, or if you have still the difficulty with the user ID password shared by them, that's not at all an issue. You can join the same link again as a guest. Okay. Third point. What about your attendance? I don't take attendance. I don't need to do that, because once the meeting keeps on going, that will automatically record your presence in that data. So once the 5-day workshop is over, okay, it will automatically give me one Excel sheet with all of your names, at which date, when did you come, when did you leave, with all the details. For example, if I read the first name in the participant like Alinjo, it will give me Alinjo. Monday, he joined at 9:30, left at 12:30, like that, it will give me row wise. Okay, from that I will take the attendance report. You don't need to separately send me an email that I have joined today as this name and all. Nothing. All that you have to make sure is that once you have joined, if at all you are joining with the given user ID like FDP_07 Ramsuri, like Ramusri, like that, that is fine, because I know in the database. If you join as a guest account, make sure your name is displayed, like Ambika Patel, Manohar Kumar, Taj Mohammed, GVS Rao, like that I can see the names. If that is enough, that's I can take from your name from the list. But if at all when you join from a device, it is showing that HP, iPad, iPhone, my iPad, like that, you have to change that. So once you have joined, the only thing you have to make sure is that go to the participant list and see if you are able to see your name there properly. If you join from your iPhone, it will show it is iPhone. So I don't know who is that. So if so, you have to change your display name there. That's the only thing you have to check. Otherwise, if your name is appearing like that, for example, FDP_Gunasekharan, I will take that. Or for example, as a guest, so that will automatically show the name in the bracket, that will show the guest. I can see several such names like say Girish Kumar and then Om Prakash Singh, Pavan Rajput. So it will showing the name, but in the bracket guest, that doesn't matter. So that will automatically, the Excel sheet will populate the name. Only thing is that if you don't update your name properly, it is showing the device name like Dell, HP, like that, you have to change that. Right. Other than that, don't worry about any attendance link and all. You come and join the session, attend it. Automatically, that will record when do you come, when do you leave. Right. Now over to you. If you have any questions, raise your hand. I will unmute one after another. Yes. Yeah, you can unmute and speak now. Nagabhushan, please go ahead. Nagabhushan, you are enabled. If you want to speak, you can speak now. Yeah.
Yes, final exam.
Sorry, say that again.
Final exam, sir. Final exam.
That will be in the Friday afternoon 2 o'clock. I have put in the brochure. So validatory session plus with the test, we have to conduct one test and upload the test marks to in the Atal portal. So I will conduct that on Friday afternoon once all the 14 technical sessions are over. Yes, Venkatesh Kumar, please.
Friday afternoon, I have class. Any extension of time will be given?
No problem. That we can adjust. It's not an issue. Yeah. Yeah, that's the only problem, right? That we can adjust. It's not an issue.
Be using mobile, sir. But as per your okay, sir.
No. If you have any schedule, we can discuss that. Not an issue. So once it is conducted, you can let me know. So I will do some alternate for that. It's not like a regular strict exam what we conduct for the students. It's not an issue. We can adjust that. Yeah. Yes, Shannon, please go ahead.
Sir, is there any feedback link for every day? No, or a final only we have to enter in Atal.
Sorry, ma'am. Say that again.
Is there any feedback link for every day, sir?
No, not every day. One link will appear in your portal after the session is over. Just you can give your feedback there.
Okay, sir. Okay.
Yes,
That's fine.
please. Yeah.
Okay, sir. Thank you.
Okay. I think, is there any? Okay, I think one more. Yes. I read the name Binu. Please. FDP underscore Binu 418. Yeah, you are enabled now. You can speak. Yeah, you can log out, Sanjay. Go ahead, please. Yeah. If you have no questions, please feel free to log out. Yes, Malay Ranjan, please.
Can you hear me?
Yes, sir. Please. Yeah.
Yeah, great. Actually, of course, I'm a professor, and I'm attending this along with my other things. Okay.
Okay.
Acha, is it possible? Can I have this copy of lectures or this thing so that I
Sir,
can go?
Once I record, that will automatically be uploaded in that Teams account. So once you log in with the credentials,
Okay.
all the
Okay.
recordings will be there. Yeah.
Acha, I can download it.
Yeah, you can download that. Yeah.
Okay, that's great. All other materials, PPT and all
Everything.
that.
So, for example, if Kuntal sharing that slides tutorial, that will be in the class materials.
Class
Another
okay.
folder recordings. So material recording will be there in the two folders.
Yeah. It's interesting. Actually, I work on antenna. I am not in this area.
I see.
But it's interesting. Many new things we are getting. This is also very important for 5G. I know. This is good initiative. Okay. Thank you.
Yes, sir. Thank you. And his question paper will be a tough one. No, I'm not here to do anything like that. Yeah, that's for a formal thing. I have to do that. Yeah. Okay, so I hope there are no other questions. So, and I can see some people are again joining in different links. Whatever the link you joined today, that is the same link for all the 5 days. Okay, so now we can disperse, and we will meet tomorrow morning 9 o'clock.